All right, hello everyone, and welcome back to our tour of the solar system. Tonight we will finally move out of the inner solar system and away from the terrestrial planets and talk about the other type of planet in our solar system, the gas giants, otherwise known as the Jovian planets. But we won't just talk about the planets themselves, we'll also talk about their system of moons, which are equally as interesting as the planets themselves. Tonight's quote comes from a person who put a lot of research into the gas giants, particularly Saturn, none other than Christian Huygens. He had a very beautiful quote, which goes, "How vast those orbs must be, and how inconsiderable this earth, the theater upon which all our mighty designs, all our navigations, and all our wars are transacted, is when compared to them. A very fit consideration and matter of reflection for those kings and princes who sacrifice the lives of so many people, only to flatter their ambition in being masters of some pitiful corner of this small spot." Perhaps Carl Sagan got some inspiration from these words of Christian Huygens when he wrote his Pale Blue Dot speech. So they're very similar in theme. All right, so here are images of the four gas giants taken from the Voyager mission. Jupiter, Saturn, Uranus, and Neptune, as well as some information about them, the distances, their masses, densities, and compositions. So they can sometimes be split up into two subcategories. Jupiter and Saturn are more traditionally gas giants, whereas Uranus and Neptune are sometimes called ice giants, and that's due to a differing composition. Jupiter and Saturn are made primarily of helium and hydrogen. In fact, their compositions are so radically different from the terrestrial planets, they're more closely aligned with the composition of the sun. This has caused some people to call Jupiter in particular a failed star, but Jupiter is actually nowhere near having the right conditions to undergo nuclear fusion in its core. In fact, you would need to increase Jupiter's mass by 80 times its current mass in order for it to become a star. So whereas some people see it as a failed star, others might see Jupiter as just a really successful planet. Meanwhile, Uranus and Neptune, more strikingly blue than Jupiter and Saturn, that is caused by a difference in composition. So they're not really made up primarily of hydrogen and helium. They are more made up of hydrogen compounds like water and methane and ammonia, with smaller amounts of metal and rock. And we'll get into those compositional differences in a little bit. But one thing I do want you to note is that the density, Saturn is considerably less dense than Uranus and Neptune. And that should make sense because the hydrogen compounds, rock, and metals that make up Uranus and Neptune are normally much more dense than hydrogen and helium gas. However, by that same logic, we would expect Jupiter to be even less dense than Saturn. But in fact, it's more dense. So what is going on there? Well, if you look at this plot where we've got the radius of the planet in Jupiter radii on the vertical and the mass of the planet in Jupiter masses on the horizontal, you can see that we've got this red curve. This is essentially telling us that the extra mass of Jupiter compresses its interior to a much higher density. So because there's just so much more mass in Jupiter, all that weight above any particular layer of its atmosphere will compress it a bit, which will increase its density. In fact, calculations have shown that Jupiter's radius is almost the maximum possible radius for a Jovian planet. If we added any more mass in the form of gas, then that compression would be so great as it would make the planet smaller. So beyond about 3 Jupiter masses, adding more mass than that, and you see the curve goes downwards, making it smaller. In fact, some extrasolar planets that are larger in mass than Jupiter have been shown to be actually smaller in size than Jupiter. And some of the smallest stars are significantly smaller in radius than Jupiter, despite being at least 80 times more massive as Jupiter. So Jupiter's a really special kind of planet there. Let's see, rotation speeds. We know that the Jovian planets, the gas giants, rotate much faster than the terrestrial planets. But Defining those rotation rates can be difficult because there are no solid surfaces of these gas giants. And it's even more difficult, as you can see in this little movie from the Voyager spacecraft when it approached Jupiter. You can see that rotation speeds vary with latitude. There are certain cloud bands that are not only rotating in opposite directions to each other, but at different speeds from one another. So how do we know the rotation speeds of these gas giants? Well, we can measure the rotation rates of the interiors of the gas giants by tracking the emission of charged particles trapped in their magnetospheres, the magnetic field surrounding those planets. That will tell us the rate of rotation of the magnetosphere, which should be the same as the rotation period in the deep interior, because that's where the magnetic fields are being generated. So by doing this, we can see that the gas giants all have a very rapid rotation rate, about 10 hours in a day on Jupiter and Saturn, and about 16 to 17 hours for a day on Uranus and Neptune. This rapid rotation also has the curious effect of causing the poles to squash and the equators to bulge, making the planets not actually perfect spheres. Saturn suffers the most from this because there's a very rapid rotation period and relatively weak surface gravity. If we go backwards to those pictures of the planets, you actually see Saturn. It does look a bit squashed. So the equator's bulging out, the poles are a bit squashed. The technical term for this shape is called an oblate spheroid. All the planets that rotate rapidly do this. So Earth is a bit squashed at the poles and bulges a bit at the equator. Venus is not. Remember, it is a very slow rotation period. Mercury, not really. Mars is a bit squashed. And then all the gas giants are a bit squashed. So it's very cool. That's a natural consequence of their rapid rotation. All right, now let's dive deep into the interiors, but we'll only do this thought experiment. You would not survive a trip into the interiors of any of the gas giants. And that's because the conditions are so weird that it's really unlike anything we have here on Earth. Computer models do tell us that Jupiter probably has some fairly distinct interior layers that don't really differ in composition. Everywhere except for the core is mostly hydrogen and helium. And the only changes that are happening are changes in pressure and temperature. So let's dive down through the cloud tops all the way down to the core of Jupiter as sort of an example of what to expect from these gas giants. So near the cloud tops, you'll find that the temperature is a brisk 125 Kelvin, which is way below freezing, about minus 148 degrees Celsius. The density is very, very low, about what is that, 2/10,000ths of a gram per cubic centimeter. And the atmospheric pressure is similar to Earth's. It's about a bar, the same as the atmosphere pressure at sea level here on Earth. But as you plunge downward, conditions become way more extreme. So at a depth of about 7,000 kilometers, the temperatures increase to 2,000 Kelvin, already way, way, way hot. And the pressure is now 500,000 times the surface pressure on Earth's. The density is about half a gram per cubic centimeter. Here, hydrogen really starts to act more like a liquid rather than a gas, which is why this layer is labeled liquid hydrogen on that figure to the left. And of course, like the rest of Jupiter, this layer also contains helium and hydrogen compounds. Going deeper, about 14,000 kilometers, we've reached a density about that of water, with temperatures near 5,000 Kelvin. This is just under the surface temperature of the sun here. And we've got pressures of nearly 2 million times Earth's surface pressure. Here, the extreme pressure forces hydrogen into a compact metallic form. And just as in the case with everyday metals, electrons are free to move around in this new creation called metallic hydrogen. So it conducts electricity quite well. This layer extends through most of the rest of Jupiter's interior. And as we'll see in a little bit, this is where Jupiter's magnetic field comes from. Finally, at a depth of 60,000 kilometers is Jupiter's core, where the temperature is about 20,000 Kelvin. not nearly as hot to fuse hydrogen into helium like the sun does. Despite the layer above it being hotter than the surface of the sun, you need to reach around 15 million Kelvin, I believe. I'm taking that off the top of my head to reach hydrogen fusion. So we're not nowhere near hydrogen fusion, even at this high temperature. The pressure is about 100 million times the surface pressure of Earth, and the density is 25 grams per cubic centimeter. And it's here the composition has changed. Now it's mostly composed of rock, metals, and hydrogen compounds. Unlike the interiors of the terrestrial planets, where they're separated into layers by composition, like core, mantle, crust, Jupiter's core is probably all mixed together. There is no difference. It's all probably a very easily homogenized group of rock, metals, and hydrogen compounds. The core contains about 10 times as much mass as the entire Earth, but is only about the same size of Earth because it is compressed to such a high density. You can see Earth's internal structure to scale there next to Jupiter's core. When so this is Jupiter as sort of a prototypical example of the interior of a gas giant. Let's look at the other gas giants now. Saturn has the same basic layering as Jupiter, just as we would expect. It's a very similar size, similar composition. But its lower mass and weaker gravity makes the weight of the overlying layers less than on Jupiter. So as a result, as we look deeper, we have to look deeper into Saturn to find each level where the pressure changes hydrogen from one form to another. That is, Saturn has thicker layers of gaseous and liquid hydrogen and a thinner and more deeply buried layer of metallic hydrogen. Meanwhile, Uranus and Neptune are somewhat different because they never really reach the pressures high enough to form metallic hydrogen. So their core material may be more liquid. It's not as compressed is what I'm trying to get at. The cores are larger in radius, even though they have about the same sizes as the cores of, even though they have the same masses as the cores of Jupiter and Saturn. And the less extreme interior conditions also allowed Uranus's and Neptune's cores to differentiate. So hydrogen compounds reside in a layer around a center of rock and metal. So even here, we can see the difference between what is sometimes called the gas giants, meaning just Jupiter and Saturn, and sometimes called the ice giants, just Uranus and Neptune. Now, where the gas giants really differ is in their source of internal heat. Remember, we've talked about internal heat a lot so far, and that is the main driver of surface geology on the terrestrial worlds. But obviously, there's no surface for these gas giants, but nonetheless, internal heat plays a role here. Jupiter has the most amount of internal heat, and it loses this heat like any object to space. But in fact, Jupiter emits twice as much energy as it receives from the sun. We're not completely confident on our answer for it, but the leading hypothesis is that Jupiter is still slowly contracting from its formation 4.5 billion years ago. We haven't measured this contraction with observations, but models of this contraction have accounted for all of the excess heat Jupiter has. So this is probably heading towards the right answer. Saturn also emits twice as much energy as it receives from the sun, but it has too little mass to still be contracting. It should have stopped contracting long ago. So maybe helium is still condensing underneath its cloud layers into a liquid at high altitudes, and that is raining down to the interior in a sort of differentiation. Remember, the conversion of gravitational potential energy in lowering that as it moves from higher altitude to lower altitude will generate some heat, will radiate away in heat. So maybe that is happening there on Saturn. Uranus emits no excess heat because so neither Uranus or Neptune have the necessary conditions to allow helium rain to form, and most of their original heat from accretion should have escaped long ago. And that explains why Uranus has no excess heat. But oddly enough, Neptune does. The only reasonable hypothesis for this is that Neptune is still contracting. But why a planet that is as small as Neptune is still contracting 4 billion years after its formation is really a mystery. We have no idea. There's still a lot of things we don't know about the gas giants here. All right, so here's the first question. Why is Saturn almost as large in radius as Jupiter, despite its smaller mass? So A, Jupiter's greater mass compresses it more, thus increasing its density. B, Saturn's rings make the planet look bigger. C, Saturn is farther from the sun, thus cooler and therefore less compact. D, Saturn has a larger proportion of hydrogen and helium than Jupiter and is therefore less dense. Or E, Jupiter's strong magnetic field constrains its size. So take a moment, pause the video, think about your answer, and come back when you've got an answer. All right, so the correct answer is A, Jupiter's greater mass compresses it more, thus increasing its density. That's what we just talked about with that plot, and how if we added more mass to Jupiter, it would actually decrease in size. That is the correct answer. All right, now let's talk about the weather of these gas giants. What are they made of? Well, the gas giants are mostly hydrogen and helium, with just a smattering of other hydrogen compounds. The most common ones are water, methane, and ammonia. But there are some small amounts of more complex hydrogen compounds like acetylene, ethane, propane, and ammonium hydrosulfide. And although they're just a small fraction of their atmospheres, these compounds are responsible for virtually all of the aspects of their appearances. Without these compounds present, these planets would be pretty much just, big balls of gray, featureless gas. Hydrogen and helium don't really do much in the color aspect there. It's because of these complex hydrogen compounds that give us these interesting colors and cloud features. So once again, let's use Jupiter as a prototypical example and investigate its atmospheric structure. Jupiter actually has a pretty similar atmospheric structure to Earth. It has a troposphere, a stratosphere, and a thermosphere. So here, the thermosphere is heated to about 1,000 Kelvin by solar X-rays and particles from Jupiter's magnetosphere. Makes sense? Let's go a bit deeper, where we enter the stratosphere. Here, there's no oxygen here. There's no ozone. Remember, the stratosphere only exists on Earth because we have the oxygen molecule, ozone, to absorb solar ultraviolet light. The other terrestrial planets don't have any oxygen in their atmosphere, so they don't have a stratosphere. Here, Jupiter has a stratosphere, not because it has oxygen and ozone, but there are some atmospheric ingredients, some complex hydrocarbons that do absorb ultraviolet light, just like ozone. And so the result is this sort of smog-like haze. That absorption gives the stratosphere a peak temperature of about 200 Kelvin, or minus 73 degrees Celsius. And then the troposphere also, just like all the tropospheres in the terrestrial planets, it also suffers from a greenhouse effect. But it's that strong heat that drives convection and explains the presence of thick clouds. So going deep, we see white ammonia clouds, then brown ammonium hydrosulfide clouds, and then even deeper, possibly it's cold enough for water to condense to form clouds. So when we look at the other gas giants, we see very similar features. Saturn has the same set of these three cloud layers as Jupiter: ammonia, ammonium hydrosulfide, and water. But the lower temperatures mean that these layers occur deeper in Saturn's atmosphere. Oh, excuse me. So, for example, to find the relatively warm temperatures at which water vapor can condense to form water clouds, we've got to look about 200 kilometers deeper in Saturn than into Jupiter. And this probably explains why Saturn has such subdued colors. Jupiter's got those beautiful bands, which we're going to talk about in a moment. But Saturn is more of a uniform kind of yellowish brown than Jupiter. Saturn's cloud layers are also separated by greater vertical distances than Jupiter's, because Saturn's weaker gravity causes less atmospheric compression. Meanwhile, Uranus and Neptune are so cold Here we've got temperature on the horizontal, where moving left is colder. Uranus and Neptune are so cold that any cloud layers similar to Saturn and Jupiter's would be buried so deep in their atmospheres that we wouldn't be able to see them. However, the colder high altitude temperatures of those two worlds allow the abundant methane gas to condense into clouds of methane snow. And the rest of this methane gas, some of which is high enough above the clouds, absorbs red light and therefore only allows blue light to penetrate deeper. And the methane clouds reflect this blue light upward, giving Uranus and Neptune their distinctive blue colors. Uranus is probably a paler blue, probably because there's more smog-like haze in its atmosphere. Probably as a result of its sideways tilt, which gives it extreme seasons. Neptune is, of course, that much deeper blue. So now we've just learned why Neptune and Uranus are much bluer than Saturn or Jupiter. All right. Obviously, Jupiter we keep using as a prototypical example, and Jupiter is certainly a planet of storms. So remember, we talked last week about the Coriolis effect of the circulation cells on Earth, where if the Earth wasn't rotating, we have two big circulation cells, one for each hemisphere. But because of the Coriolis effect on Earth, each of those big circulation cells are split into three smaller ones. Now, Jupiter also has a Coriolis effect in circulation cells, but because Jupiter is so large and it's rotating so fast, those circulation cells are split up into many, many, many smaller circulation cells. So we get alternate bands of rising and falling air, which is why we see these different bands of clouds. The different colors here, I'll press play on this little GIF, you see the clouds moving. The different colors are created by different molecules. We've got red-brown ammonium hydrosulfide, which is lower down in falling air, and white ammonium clouds further up in rising air. So you can now actually see these clouds. So this brown must be falling. Then on either side of it is rising air, where we're seeing the tops of those ammonia clouds. Then another falling band where we're seeing ammonium hydrosulfide next to some rising ammonia clouds. You might wonder why the ammonia clouds only form in the rising air and not the falling air. The answer goes back to the clouds themselves. Jupiter's lower atmosphere has ammonia throughout. So there's always ammonia in the air rising upward. However, once the ammonia condenses to form clouds of ammonia ice, those ice flakes fall back down as ammonia snow. So the air that continues to rise above the clouds has very little ammonia left in it. Therefore, when this ammonia-depleted air spills to the north and south and returns downwards in the bands of falling air, there's not enough ammonia to form clouds. So that's why we see the deeper ammonium sulfide air. Obviously, they're also not just these distinct cloud layers, they are clearly also interrupted by these big, ginormous storms. The most famous one of which is, of course, the Great Red Spot. The Great Red Spot has been reported for centuries. Galileo observed it, so we've known it existed at least since the 1600s, and it's still going strong. The storm itself takes about 6 days to complete a rotation, circulation of its air. It's about twice as large as Earth. You can see there on the left a beautiful high-res image of the eye of the storm taken by the Juno spacecraft. And then on the bottom is from the Voyager spacecraft. But there's not just the Great Red Spot on the planet. There are also brown ovals, which are low pressure storms, and white ovals, which are high pressure storms. No one actually knows what is driving these storms, why Jupiter has only one Great Red Spot, or why the Great Red Spot has lasted so long. We don't even know why the Great Red Spot is red. And that's a mystery to us. It's one of the most famous features in the solar system, and we named it for its color, and we have no idea why it has that color. We just have no clue. There are some theories, obviously. We're not completely lost, but nothing concrete. We don't know. Two other long-lived storms have recently been observed to change color, going from white to red. One particular storm recently, in 2008, you can see here in these three images, got too close. It got in between a white oval and the Great Red Spot, and you can see it moving closer and closer, and it actually got torn up by the Great Red Spot, a little bit absorbed. There, a little remnant of it there to the right of the Great Red Spot. So the storms on Jupiter are a mystery, but they are certainly powerful and noticeable. There's still a lot of questions we left unanswered. When we look at the other gas giants, we do see evidence of storms on all the other gas giants. So just like on Jupiter, Saturn's rapid rotation also creates alternating bands of rising and falling air, along with rapid east-west winds. In fact, Saturn's winds are even faster than Jupiter's, which is something that scientists have yet to explain. We don't know why that is. Some seasonal changes have been noted on Saturn, but Saturn's internal heat kind of keeps the temperatures the same year-round and planet-wide. Neptune also has very faint dark bands, and it even had a storm like Jupiter. We call it the Great Dark Spot. We only discovered it when Voyager 2 flew past Neptune, but we looked back at Neptune 6 years later with Hubble, it was gone. So clearly there's something happening on Neptune that is causing its storms to last significantly shorter than the storms on Jupiter, and we're not sure what's going on there either. Uranus was most striking. It was completely blank when Voyager 2 flew past in 1986. Although more recent observations have shown that there are storms brewing underneath the surface as Uranus enters summer in its northern hemisphere. It only started entering summer in 2007. It takes 84 years for it to orbit the sun. So its seasons are going to last pretty dang long. But as it continues to be in summer, its northern hemisphere continues to be in summer, perhaps there'll be more storms on Uranus. I'm not sure. All right, here's a question. Why do Uranus and Neptune appear blue? A, oceans that are visible through their atmospheres are blue. B, the nitrogen gas in their atmospheres absorb red light. C, the methane gas in their atmospheres absorb red light. Or D, small dust grains preferentially scatter blue light. So think about your answer, pause the video, come back when you got an answer. All right, the correct answer is the methane gas in their atmospheres absorb red light, which causes them to be blue. All right, we're going to talk about the magnetospheres. Jupiter has the strongest magnetosphere of the gas giants, about 20,000 times stronger than the Earth's. And that is caused, remember, the qualities you need to generate a magnetosphere. You need an interior region of electrically conducting fluid. You need convection in that layer of fluid, and you need at least moderately rapid rotation. And Jupiter has all of that in the form of the thick layer of metallic hydrogen. And of course, it is also rapidly rotating, only about 10 hours for a day on Jupiter. So it gets this very, very strong magnetosphere. In fact, the magnetosphere stretches out to nearly 40 times Jupiter's radius. So it's very big too. If we could see it on the sky, it would be larger than the full moon on the sky. Jupiter also traps Jupiter's magnetosphere also traps far more particles than the Earth's does. The Earth's, the only particles that gets trapped in the Earth's magnetosphere are particles from the sun. But here, Jupiter can rely on its moons to also feed its particles. So its most volcanically active moon, Io, contributes many additional particles as those volcanoes erupt. Those particles go into creating the auroras on Jupiter. And in turn, the magnetic field affects Jupiter's moons by depositing and stripping some particles from those moons, changing the compositions, and perhaps doing some other things there as well. If we look at the other gas giants, they all have magnetospheres, although much weaker than Jupiter's due to smaller layers of electrically conducting material in their cores. They all also have aurorae. You can see the aurorae on Saturn's North Pole there. These magnetic fields are generally thought to be aligned with the planet's rotation axis, which is true for Jupiter and Saturn, but not for Uranus and Neptune. You can see Here, the red line is the magnetic axis. The white line is the rotation axis. Very similar for Jupiter and Saturn. Here, wow, that's a huge difference between those two axes on Uranus and Neptune. We don't know why. We have no idea. That's another thing we've got to explain. Now let's get into talking about the system of moons around each planet. We'll start with Jupiter. The four biggest moons for Jupiter are the Galilean moons, since they were discovered by Galileo. So the closest one in is Io, and it is by far the most volcanically active world in the solar system. Volcanoes dot the surface with eruptions constantly repaving the surface. So there's not many craters around. In fact, we have spacecraft that have caught these eruptions happening. That little GIF down there is a volcano erupting on Io with a plume of material. These eruptions are constantly outgassing sulfur dioxide, sulfur, and some sodium, which are then ionized and go on to be trapped in Jupiter's magnetosphere. Now, Io's active volcanoes tell us that it's got to be pretty dang hot in the inside. However, Io is only about the size of our very geologically dead moon. So it should have long ago lost any internal heat it had. The only possible answers to why it is still volcanically active is from tidal heating. So Jupiter's tidal force, combined with Io's elliptical orbit, squeeze and stretch Io, constantly pumping it full of energy, which generates friction and keeps the moon warm. Now, we're left with another question there, however. Why is Io's orbit slightly elliptical when almost all the other large satellites have nearly circular orbits? Well, that's because Io's orbit is elliptical because it is in orbital resonance with the other Galilean satellites. So here's a little GIF I made of Io in green, Europa in yellow, and Ganymede in purple. And this orbital resonance means that these moons line up periodically. You just saw it happen there. For every 4 Io orbits, Europa has orbited twice and Ganymede has orbited once. So as these moons continue to line up, their gravities will align and will pull Io's orbit to make it slightly more elliptical than the other moons. That gives it its changing tidal force as it orbits Jupiter, which pumps it full of energy, making it more volcanically active. Let me know if you have any questions about that. Moving on, Europa is very different from Io. In stark contrast to Io, Europa is an icy world, likely covering a global subsurface ocean. You can see here that it's got tons of cracks in the surface, and this is most likely caused by liquid water rising up and freezing, making the surface look like a bunch of icebergs frozen in place. You can see a very detailed image of the surface that looks very much like ice there. Europa also has an induced magnetic field, which is only possible if there is a layer of salty liquid water underneath the surface. And it likely remains liquid for the same reason that Io is volcanic, because of tidal heating. Although this will be much weaker since it is further away from Jupiter and its orbit is not as elliptical as Io's. This begs the question that if it has a hot interior to keep this layer of water liquid instead of just frozen ice all the way through, it seems reasonable to imagine that maybe there are volcanic vents that dot the ocean floor that sometimes erupt, perhaps leading to the formation of subsurface lakes within the icy crust, which would then cause the cracking of the icy surface. If these ideas are correct, then Europa may have a hidden ocean containing more than twice as much liquid water as all of Earth's oceans combined, along with a seafloor dotted with the same types of volcanic vents that exist in Earth's oceans. maybe life has even evolved to survive around those volcanic events. So we desperately want to get to Europa and go ice fishing, see if anything comes up and bites the camera. Moving further out, Ganymede is the king of the moons. It's the largest moon in the solar system. In fact, if it were not orbiting Jupiter and instead were orbiting the sun, we would probably call it a planet. I think it's bigger than Mercury. So it is really the king of the moon. And it has a dual age surface. You can see here the difference between the dark and the light regions. The dark regions are heavily cratered, suggesting an older age, while the lighter regions have very few craters, likely erased by, once again, frozen water. You can see here a little zoom in of the difference between the dark regions on the left and the lighter regions on the right. And you see the difference in the surface features there, where the jagged lines are likely where liquid water has come up and froze, just like it happens on Europa. Ganymede also has a magnetic field, likely, once again, induced by a salty liquid subsurface ocean. Although this ocean's got to be much deeper than on Europa. That came from studies of this induced magnetic field. Once again, what causes Ganymede to be so hot? Because Ganymede is farther from Jupiter than Europa, I know the tidal heating there is much, much weaker and could not by itself supply enough heat to melt the ice today, giving it a subsurface ocean. However, Ganymede's larger size means maybe it's retained more heat from radioactive decay. So maybe tidal heating and radioactive decay have combined to provide enough heat to make a liquid layer beneath the icy surface. Maybe that's that. And then finally, the last Galilean moon is Callisto. It doesn't participate in the orbital resonance of the other three Galilean moons, and it's not as active. It looks pretty much it looks like what we'd expect from an outer solar system satellite. It's just a heavily cratered ice ball. In fact, it's so heavily cratered that any new crater would erase old craters on Callisto. The craters there, that means that the surface is very, very old. There's no volcanic or tectonic features, so it has no internal heat. There is some dark powder in some low-lying areas, likely debris left behind when ice vaporizes into a gas. And Callisto might also have a liquid subsurface ocean, although it is unknown how it would remain liquid. But there are signs that it might have a subsurface liquid ocean. So, wow, if so, then we face a very intriguing possibility that there could be oceans on 3 worlds orbiting Jupiter with far more water than what we find here on Earth. So in the future, if water becomes scarce on Earth, we might have to go mining the Galilean satellites for some water. Moving outwards to looking at Saturn's moons, we come to one of the most interesting moons in the solar system and Saturn's largest, and that is Titan. Titan is unique among all the moons in the solar system for being the only one with a substantial atmosphere. So this yellowish color of Titan, that's not the surface. We are looking at an atmosphere, 90% molecular nitrogen with a smattering of argon, methane, ethane, and some other hydrogen compounds. In fact, both methane and ethane are greenhouse gases. So Titan's surface is warmer than it otherwise would be, but it's still very cold, 93 Kelvin or about minus 292 degrees Fahrenheit. But that slight warming creates some intriguing effects on the surface. And we can see hints of that in the image on the right. So that bright spot up at the top of Titan is not in its atmosphere. That is sunlight reflecting off of a lake of liquid something on the surface of Titan. And that image is just so cool to me. I absolutely adore that image. What is that liquid something? Well, the temperatures are warm enough and the atmospheric chemistry is such that it produces temperatures warm enough for methane and ethane rain. So we got lakes and oceans of liquid methane. And its atmospheric chemistry is interesting because it produces tons of organic compounds. Those are the ingredients necessary for life. Titan is the furthest world from the sun for which we have put a lander on. When Cassini first entered Saturn's orbit um, in 2004, 2005, it carried with it a probe called Huygens, which is why I picked Christian Huygens for the quote tonight, that it deployed to Titan's surface in 2005. And you can see the image Huygens got sent back for us there on the right. You can see a hard crust. It's a bit squishy below, perhaps with like sand with liquid mixed in. And photos showed these ice boulders surrounded by erosion. And all of these results support the idea of a wet climate, but wet with liquid methane rather than liquid water. And more observations of Titan using radar imaging from Cassini have shown us these lakes. So on the left is the shoreline of one of the largest oceans on Titan called Kraken Mare. The ocean is the black stuff, and then you get the land in the lighter colors. And you can see archipelagos, shorelines, river deltas, bays. You can see all the features of all the geologic features that we see here on Earth when water interacts with land, as that you see on Titan as liquid methane interacts with the land. On the right, sorry, in the center of this slide, you can see one particular sea that if you look at these smaller inset images where the arrows are pointing, you can see that as the tides and conditions change, islands come into and out of existence. Like, this is beyond cool, guys. This is amazing. That liquid exists on other planets, on other objects aside from the Earth. The most astonishing result, most probably, is how familiar the landscape looks. I've already sort of mentioned that. Instead of water, Titan has liquid methane and ethane. Instead of rock, Titan has ice. Instead of molten lava, Titan has a slush of water ice mixed with ammonia. Instead of surface dirt, Titan's surface has smog-like particles that rain out of the sky and accumulate on the ground. Evidently, the similarities between the physical processes that occur on Titan and Earth are far more important in shaping the landscape than the fact that the two worlds have very different compositions and temperatures. Now, the abundance of organic molecules on Titan, along with the similarity in its surface geology to Earth, makes it natural to wonder whether Titan could be home to life. And we can't really rule that out without really doing way more in-depth landing missions for Titan. But we tend to think it's unlikely because, first of all, the temperatures of Titan are very cold, but also the chemical properties of liquid methane and ethane make it less feasible for them to support the biology of life than liquid water. So probably not life existing on Titan, even though we can't concretely rule it out. There are other interesting moons around Saturn. These are the 6 medium-sized moons. We got Mimas, Enceladus, Tethys, Dione, and Iapetus. Only Mimas, the smallest of these 6, shows evidence of past volcanism or plate tectonics. It's essentially a heavily cratered ice ball, but it has one huge crater that's nicknamed Darth Crater because of its resemblance to the Death Star from Star Wars, although the crater's official name is Herschel, but we can call it Darth Crater. That probably came close to tearing Mimas apart. But most of Saturn's other medium-sized moons are pretty heavily cratered, suggesting that they lack global surface activity. However, on some moons, we do find evidence of volcanism or tectonics that occurred towards the end of the late heavy bombardment period. So there are smooth regions appear in places where icy lava once flowed, and bright streaks, like on Dione here, you see some bright streaks there, might be these spectacularly vast tectonic cliffs running parallel to one another. Iapetus looks pretty bizarre, has this kind of dual color here, a very light region and then a dark region. It's got a ridge more than about 10 kilometers high that spans nearly half of its circumference. And this dark dust actually comes from another of Saturn's moons, Phoebe. that's too small to hold on to material if it's ever impacted. So that impacted ejected material falls back onto Iapetus. Enceladus is an even bigger surprise. This moon is only about 500 kilometers across, big enough to fit inside of the state of Colorado. But it shows clear evidence of ongoing geological activity. So the surface has very little impact craters, and some regions have none at all, telling us that recent geological activity has erased impact craters. Moreover, these strange grooves here are measurably warmer than the surrounding terrain. And photographs show this region venting huge clouds of water vapor and ice crystals, some containing salt. Those fountains must have some subsurface source, which could potentially mean the existence of an ocean, which would also make us wonder about the potential for life beneath the icy crust. The internal heat on Enceladus comes from tidal heating through an orbital resonance with Dione. Although scientists were definitely surprised to learn that the heating is strong enough to make Enceladus still active today. When we come to the medium-sized moons of Uranus, we got Miranda, Ariel, Umbriel, Titania, and Oberon. And like the other Jovian moons, they're all largely made out of ice. But our only close look at these moons came from the Voyager 2 flyby in 1986, which actually left us with way more questions than answers. For example, Ariel and Umbriel are virtual twins in size, yet Ariel shows evidence of volcanism and tectonics, while the heavily cratered surface of Umbriel suggests a lack of geological activity. Titania and Oberon also are twins in size, but Titania appears to have had much more geological activity than Oberon. We don't really know why these two pairs of similar sized moons should vary so greatly in geological activity. And Miranda, which is the smallest of these five, is the most surprising. We might expect Miranda to be heavily cratered, like Saturn's similarly sized moon Mimas. But instead, images show Miranda to have these huge tectonic features and relatively few craters. Why would Miranda be way more geologically active than Mimas? Our best guess is that Miranda had an episode of tidal heating billions of years ago, perhaps during a temporary orbital resonance with another moon of Uranus. Mimas never had such an episode of tidal heating, so maybe that's why they're different. But there's still so many unanswered questions. Uranus and Neptune have not been visited since the 1980s, and it really shows with how much we know about these worlds. When we look at Neptune, Neptune has one big moon. It has many moons, but there's one big one that we're going to talk about, and that's Triton. So don't get us confused with all the other moons that sound similar. We've got Titan, Titania, and Triton all around different planets. So Triton may look like a typical moon, but it orbits Neptune backwards and at a high inclination relative to Neptune's equator. So if Neptune's equator was like this, Triton orbits like this. This all suggests that it was actually captured rather than formed near Neptune. So it was most likely part of a binary Kuiper belt system, just like Pluto and Charon, which we'll talk about next week. There's more like a binary system that interacted with Neptune. So Triton lost energy and fell into an orbit while its partner gained energy and was flung away, probably out of the solar system. Triton also has geological activity in the form of some past volcanism and tectonics. That's very cool. So we're left with, why are small icy moons more geologically active than small rocky planets? Well, when we look at the terrestrial planets, the internal heat comes from radioactive decay, and that can cause volcanic and tectonic activity, but only the large planets retain enough internal heat to stay geologically active. Meanwhile, when we look at the moons, tidal heating can cause tremendous geological activity. And even without tidal heating, icy materials can deform and melt at lower temperatures than rock, increasing the likelihood of geological activity. And together, those effects explain why icy moons are much more likely to have ongoing geological activity than rocky terrestrial worlds of approximately the same size. So that explains why these moons are oddly way more geologically active than some of the terrestrial planets. Here's the final question of the night. There are large straight cracks in the icy covering of the moon Europa. These are thought to be due to A, the slow expansion of Europa due to its hot interior, B, the fact that the ice sits over an underlying ocean of water, C, the gradual contraction of Europa due to differentiation in its interior, D, long cracks spreading out from the many impact craters on its surface, or E, none of the above. So think about your answer, pause the video, come back when you got an answer. All right, the correct answer is B, the fact that the ice sits over an underlying ocean of water. The last thing we're going to talk about are the rings. Saturn is most famous for its rings. They're very easily visible just with telescopes you can buy at Walmart here. You can see the rings of Saturn. Saturn's rings are made primarily of water ice that reflects the light back to us. And these rings are made up of particles that range in size from dust grains to large boulders. So the top right image, the rings are colored depending on the size of the particles. So purple color means the particles are greater than 5 centimeters, or about 2 inches. Green is particles less than 5 centimeters, and blue is particles less than 1 centimeter. All these particles essentially orbit Saturn at the same speed in the same direction. So when they collide, it's more like gentle nudging rather than, smattering impacts. And they do collide with each other every few hours. And just like in the formation of our solar system, the rings of Saturn, these particles collide and stick together until something else hits them, maybe an outside impact or another ring particle, and they'll split up again. This happens over the course of several hours. These rings are incredibly thin. They're one of the thinnest astronomical structures. Despite spanning more than 270,000 kilometers diameter, they are only a few meters thick. It is beyond thin compared to the size that they are. When we look at the rings of Saturn in detail, we see an astonishing number of rings, gaps, ripples, and other features, as many as 100,000 altogether. We're still kind of struggling to explain all of these features, but some general ideas are now clear. So you can see the full extent of Saturn's rings, and some that are named gaps. We've also named some of the rings, creative names like A ring and B ring and F ring. The rings and gaps are caused by particles bunching up at some orbital distances and being forced out at others. And this bunching is a natural consequence of gravity. One source of nudging comes from small moons located within the gaps of the rings themselves, sometimes called shepherd moons or gap moons. The gravity of a gap moon can effectively keep the gap clear of smaller particles while creating ripples in the ring edges, which you can see here on the left. You can see, I forget which moon this is. I think it might be Dione, creating actual vertical ripples in the rings ahead and behind it. Ring particles can also be nudged by the gravity from larger, more distant moons. So for example, a ring particle orbiting about 120,000 kilometers from Saturn's center will circle the planet in exactly half the time it takes for the moon Mimas to orbit. So every time Mimas returns to a certain location, the ring particle will also be at its original location and will therefore experience the same gravitational nudge from Mimas. Those nudges reinforce each other and clear a gap in the rings. In this case, we call that gap the Cassini division. That's the cause of that division. This right image is actually material being ejected off of Enceladus and going into and feeding into the ring system around Enceladus. When we look at the other gas giants, they all also have rings. We didn't know about Jupiter's rings in the top left image until Voyager came around in 1979. Voyager 2 saw Uranus's rings in 1986 and Neptune's rings in 1989. We knew about Uranus's rings before Voyager, though, in 1977, because of what is known as a stellar occultation, where as Uranus moves across the sky, it will pass in front of a star. And it is aligned so that instead of Uranus blocking the star entirely, the rings pass in front of the star. And the star will blink in and out. And that told us that Uranus had 9 thin rings. Similar observations of stars passing behind Neptune told us about Neptune's rings. But those are more confusing because Neptune had, unlike the same density throughout as Saturn's rings, Neptune's rings are more dense in some regions than others. So they're more like arcs rather than rings. We don't know why that happens. But that was very confusing when we observed that back in the late 70s. Where do these rings come from? The rings most likely come from the small moons orbiting each of these planets. Tiny impacts of these moons release particles from those moon surfaces, and those released particles become new dust-sized ring particles. Ongoing impacts ensure that some ring particles are present at all times. Also, larger impacts can shatter a small moon completely, creating a supply of boulder-sized ring particles. And then frequent tiny impacts can slowly grind those boulders into smaller ring particles. Some of those particles are recycled to forming small clumps, only to come apart again later on. Others are ground down into dust and slowly spiral onto their planet. In summary, all the ring particles ultimately come from the gradual dismantling of small moons that formed during the birth of the solar system. So that's how we get these beautiful, beautiful ring systems. And that sort of concludes our tour of the Jovian planets. So next week, we'll talk about all the smaller things of the solar system, the asteroids and comets and the dwarf planets. And then we'll move beyond our solar system entirely and talk about other solar systems around other stars. And then we'll be done with talking about solar systems in general. So I look forward to seeing you all next week. Definitely comment down below if you're enjoying these. If you have any questions, certainly leave those in the comments. Give it a like, subscribe, becoming a typical YouTuber now. And I will see you next week.